Hi, welcome to a new lecture covering the foundations of machine learning. Today, we'll be looking at logistic regression in detail. Specifically, we'll be learning the theory behind logistic regression, how do we calculate losses, and how to update the parameters such that you can finally have a model that fits the data. And finally, in the second part of the lecture, we'll be implementing logistic regression using code in Julia. And this will be from scratch without using any existing packages. So imagine we have a data set that looks like this. We have a bunch of people, and the people are classified into diabetic or non-diabetic category. On x-axis, here you have blood glucose level in milligram per deciliter, and it is kind of ranging from somewhere close to 100 all the way till maybe 175, 160, something like that. And you can see that these green people are denoted on y-axis by 0, and these red people are denoted on y-axis by 1. So 1 means diabetic and 0 means non-diabetic. So you can already see that this is a binary classification where people with diabetes is classified as 1, people without is classified as 0. Now consider the following situation where if a new data point is given, a new data point can be anywhere on this x-axis, right? It can be a person with glucose level in the blood maybe 200, which is very high. It can be someone with blood glucose level 65 or 70 milligram per deciliter. So the new person, the value assumed by the new person can be anywhere, any continuous value within a given range of possible blood glucose levels. And the task is to make a classification whether that person belongs to diabetes or non-diabetic category. So this is a classification problem where you are training a model. You have to train a model from the given data so that for future data points which are not part of the training, you can make accurate, meaningful predictions. So that's the question here. If someone has 120 milligram per deciliter, is that a diabetic person or not? And we know that this 120 milligram per deciliter would fall somewhere over here. 120 means it would be somewhere like this. And you might be tempted to say, oh, okay, this looks like a person. When I say here, I don't mean here. I mean anywhere here on the x-axis. Now, the question is, will that person be here or will that person be here? Maybe you might be tempted to say that this person is non-diabetic. If that's the case, what about if a person is over here? Like 130, let's say 130 milligram per deciliter or 128, whatever it is. Will that person belong to diabetic category, non-diabetic category or diabetic category? It's hard to say. So in cases like this, where the decision boundary is not very clear, and if the task is classification, you can use logistic regression. And logistic regression is, in this particular example, we are looking at binary classification. But we know that classification did not always be binary. There could be more number of classes. We have data available from both the classes, right? We have diabetic people and non-diabetic people. And now we are making predictions on unknown data points. So let's look at the logistic regression, which is going to do this for us. It's very helpful for such classification tasks. In this lecture, we'll be only looking at binary classification, but of course, other classifications are also possible. But let's see how we can predict the probability of a class, probability of a new data point for it to be in class 1 or class 0. So if we had a linear regression, you will forget about this particular curve. So let me move it here. If you were using linear regression on this data points, it can simply draw a line. And maybe the line that minimizes the mean squared error, which we have learned in the previous part of this course, MSE, is probably something like this. It won't be like this because then the line is so far away from all these points. It won't be like this because then the line is far away from all the points. It also won't be like this because now it's far away from green points. So probably the line will pass through the points in something like this fashion. And the problem with this is that this is not a good fit at all because you need two classes. And this line is not a model which helps to distinguish that you have two classes. Maybe you might be tempted to say, okay, you can have this as the line. And then you say, whenever the y value of the line is greater than 0.5, you say that it belongs to class 1. And if the y value of the line is less than 0.5 here, you will say that it belongs to class 0. You might be tempted to say this, but you agree that this line is not fitting the data points really well. So what may happen is that for this particular, the x value corresponding to this guy is actually over here. And the y value for the line is less than 0.5, which means now this point is classified as non-diabetic, although this is actually diabetic. What about this guy? The x value is somewhere here, y value on the line is here, and then you will be again classifying it as non-diabetic because the y-axis value of the line is less than 0.5. Now, so you can already see the issue. Like even in the training, the accuracy is very difficult to be close to 100%. In testing for new data sets, it will be impossible. So now this brings us to a question that, okay, if we had a function like this, wouldn't this be slightly better? Because now what we can do is we can say that, okay, this function is fitting through the points fairly well. And wherever it's not fitting is in this transition point. So I can pull the function a little bit like this. I mean, it's not perfect. This is exactly not how the sigmoid, which is the name of this curve, is supposed to look like, but you get what I mean. So here the function is going through almost all the points on the y equal to 0, that kind of points. And the function is fitting the non-diabetic patients. And here the function is again fitting the diabetic patients. And then you can say that, okay, if the value of the function, if the y-axis value of this function is greater than 0.5, you can say that, oh, all those people belong to diabetic category. And if it is less than 0.5, all those people belong to non-diabetic category. So let's see how to implement this. So essentially what we are doing is we want to convert the linear regression into something that looks like this sigmoid or S-shaped curve. So that's what we are trying to do. Before all of that, let's just look at some properties of sigmoid. So we want the data to fit from on y-axis from 0 to 1, right? Because you want to move all the things, all the data points above y equal to half or y equal to above y equal to 0.5 to be belonging to class 1. And all the data points where y value is less than 0.5 will belong to class 0. That's what you ultimately are going to do. So you want the sigmoid to be constrained between 0 to 1 on y-axis. And on x-axis, as the value of x decreases, the sigmoid value gets close to 0. As the value of y increases, as the value of x increases, the sigmoid curve approaches close to 1. And the equation for this is 1 by 1 plus e raised to minus x, if provided this is x and this is y. So this is y equal to 1 by 1 plus e raised to minus x. What if we had something like y equal to 1 by 1 plus e raised to minus x plus 2? Then whatever x equal to 0 was accomplishing, which is the middle of the sigmoid, now x equal to minus 2 is accomplishing. Meaning the sigmoid curve has to be shifted slightly here, right? Because x should be minus 2 in this case for the sigmoid to perform similarly. What if we had, instead of x plus 2 here, we had x minus 2? Then it will be a sigmoid that is shifted towards here, such that the half point of the sigmoid is coming at x equal to plus 2. And you can also add other quantities like a coefficient with x. So for example, you can add 3x minus 2. Then overall, that will also affect the shape of the sigmoid. So basically here, x is like any linear term. It could be of the form in general, mx plus e. So that is what we are going to do here. So we assume that z equal to mx plus b is the term where m and b are the parameters that we have to optimize. And we say that y equal to 1 by 1 plus e raised to minus z is the sigmoid curve that we have to obtain. And what is this? This equal to 1 by 1 plus e raised to a minus mx plus b. So here x is the x-axis value, and that is going to give us the value of y. And the only two parameters that we have liberty to play with are m and b. So our goal in doing a logistic regression is finding the values of m and b such that the predictions y are matching, or they are very close to the actual values of y, which is denoted as just y. Predictions are denoted by y cap. Actual values of y are denoted by just y. And we will say that if the prediction y cap is greater than 0.5, then the class is 1. And if the prediction y cap is less than 0.5, then the class is 0. So this is what we want to accomplish through logistic regression. Now we will see how to implement this mathematically. So algorithmically, let's see what are the steps that we have to follow. So first we start with random values of W and B. So what is W and B? W and B is exactly same as these two guys, M and B. So so here I have used M for slope and B for intercept. Here I'm just writing Z equal to Wx plus B in this format. Fairly straightforward. So you start with random values of W and B. So maybe you start with W equal to 0 and B equal to 0. And that will help you get a value of Z. And then you substitute the value of Z in this expression, Y cap equal to 1 by 1 plus e raised to minus Z. And then calculate Z and then calculate Y cap. And then calculate loss. And what is loss? It should depend on the difference between Y and Y cap. Not exactly like this, not exactly Y minus Y cap, but it has to be somehow related to the real value of Y, the difference between real value of Y and predicted value of Y, or vice versa, the difference between predicted value of Y and real value of Y. Now, this difference or this loss will help us calculate the change that we have to bring in W and B. It may be positive or it may be negative. And then we modify W and B based on this calculated value of change and also by using a learning parameter, which you will see soon. And then you repeat the process. Once you modify W and B, you again calculate Z, then you calculate Y cap, then you calculate the loss, which is the difference between Y and Y cap. Then you again calculate delta W and delta B, and then you repeat this until a point where the loss is minimized or the loss reaches a value which you are comfortable dealing with. So this is the algorithm that we'll be following to implement logistic regression. All of this is good, fairly straightforward. Now, a good question that you should ask here is, what exactly is the form of this loss? So in the past lecture, which was on linear regression, we saw that the loss is in the form of mean squared error, MSE. What exactly is this mean squared error? It's nothing but how far away every single point on an average is from the model. So if you have 6 data points like this, the model, which is a straight line in linear regression, will pass through the points somewhat like this. Now, mean squared error is the mean of square of errors. So what is the square of error? Square of error is Y predicted minus the real value of Y, which I was previously writing as equal to Y predicted is Y cap, Y cap minus Y the whole square. This is for individual value of the dot. So here you have I running from 1 to 6. So you have I equal to 1 to n, where n is the number of points. And then you divide by n. Why? Because you want the mean value. So you are calculating the square of error, that is the SE, square of error, and mean value, mean of the square of error, which is why you have sigma and divided by n. Now, let's see what is the problem with using mean squared error in this particular case. So in this case, what was the predicted value of Y? Y predicted or Y cap is equal to sigmoid of, so this is not sigma multiplied by, so please don't read it like that. This is sigmoid of Wx plus B. And Wx plus B is nothing but Z. So it's sigmoid of Z, which is equal to 1 by 1 plus e raised to minus Z. So this part is fine, right? Now, imagine that the loss was defined using mean squared error, although the whole point that I'm trying to say here is that mean squared error is not a good metric. But I want to show you mathematically why. So here, imagine that in the case of logistic regression, where the output is of the form 1 by 1 plus e raised to minus Z, where Z equal to Wx plus B. So W and B are the parameters that we are trying to optimize. In that case, the mean squared error, if we were to define that, it will look like Y real minus Y predicted, the whole square, assuming there is only one data point. Let's simplify things so that we assume that there is only one data point, not like n data points. So submit the sigma, the symbol is not coming. Now, this is what? This is equal to Y real minus sigma of Z, the whole square, because the predicted value of Y is nothing but sigma of Z. Now, what are we trying to do here? We are trying to reduce or minimize the mean squared error while we optimize for Z or while we optimize for W and B. So the fact that we are writing here the equation in terms of Z or Z is implicitly making you optimize the terms W and B. So basically, if you want to optimize, what do? You first try to calculate the derivative. So dou MSE by dou Z, which is the partial derivative of mean squared error with respect to Z. And this is easy to do because dou by dou Z of this is 2 times YR minus sigma times minus 1 multiplied by dou sigma by dou Z. So sigma prime here, sigma prime equal to dou sigma by dou Z, right? So that is what I have written here. This minus sign is coming because here you have YR minus sigma. Now, what is sigma prime? Dou sigma by dou Z. Since sigma only depends on Z, you can write this as d by dz or d by dz. So d by dz of 1 by 1 plus e raised to minus z, which you can also write as 1 plus e raised to minus z raised to minus 1. So now it's easy to calculate the derivative. It will be minus 1 times whatever is the derivative of this, which will be minus e raised to minus z, the whole raised to minus 2. And since there is the whole raised to minus 2, I'm bringing it in the denominator here. So it will become of this format, which will be this in the simplified form. And you can write e raised to minus z as, so you know that sigma equal to 1 by 1 plus e raised to minus z, and which means 1 by sigma equal to 1 plus e raised to minus z, which means e raised to minus z equal to 1 by sigma minus 1, right? So that is what I have written here. So this e raised to minus z, I have substituted with 1 by sigma minus 1. And then this guy is what? This is basically 1 by 1 plus e raised to minus z the whole square, which is what? Which is sigma square. So then if you expand, if you multiply sigma square to both terms, and then you take sigma outside, or rather you just multiply, you take 1 sigma inside. So this will become 1. This term will become 1 because sigma square, one of the sigma from the square will come inside. Sigma and sigma will cancel. So this will become 1 and this will be minus sigma. So ultimately, the shortened format of this will be sigma times 1 minus sigma equal to sigma times 1 minus sigma. And what is this? This is d sigma by dz, right? Okay. So now, what is dou by dou z of mean squared error? We have this as the term for mean squared error's derivative. And for sigma prime, you substitute this term, sigma times 1 minus sigma. So that is what I have done here. So this is dou mean squared error by dou z. Fine. So we have an expression for mean squared error's derivative. Now, do you see one thing here? Here there is a small problem. In fact, not small problem. This is a problem that affects many machine learning models. The issue here is that if the value of z is much greater than 1, so imagine it's like 10, 15, whatever, like not like a high value, but even normal values of z, as value of z increases, sigma will be closer and closer to 1, and which means that 1 minus sigma will be closer and closer to 0. And 1 minus sigma is this term, which means if this guy is closer and closer to 0, the derivative will be closer to 0. And this is called as vanishing gradient. And what is the problem if the gradient is trying to vanish? Because then if gradient is not there, the terms w and b, which is what we want to optimize, will not change, because the delta w and delta b is literally proportional to the gradient dou msc by dou w and dou mse by dou b. And this is also proportional to because w and b are parameters within z. This is basically delta w and delta b change that each iteration will bring to w as well as b is proportional to the gradient. And if gradient is vanishing, then you can't update the weights or bias. Similarly, if z is much less than 1, in fact, not 1, much less than 0, which means negative. Let me just draw here. If z is much less than 0, then sigmoid function, because sigmoid function is like this, right? If z is much less than 0, which is negative, then sigma of z will tend to be 0, because y-axis value will be close to 0, which means, again, dou mse by dou z will tend to 0. Why? Because this guy will tend to be 0. So this is the vanishing gradient problem that exists if you use mean squared error as the loss function in logistic regression. Because mean squared error will make the gradient vanish both when z is much greater than 1 or if z is much less than 0. So for high positive values of z or high negative values of z, the gradient is vanishing, which means the weights will not get updated. So the model will have a very, very hard time learning something meaningful from the data points, from those data points which are far away from origin. Model can only learn from those data points which are closer to origin. Now, this is the reason why we should use something called as cross entropy loss. I'm sure you have heard of the term cross entropy loss. You may or may not be familiar with it. Cross entropy loss is very routinely used in problem statements where you are trying to classify something. So here you are not using mean squared error. Mean squared error is very commonly used in regression. Cross entropy loss is very commonly used in classification. So let's see what cross entropy loss can do, which this mean squared error could not do. So cross entropy loss, the equation for that is nothing but minus sigma y times logarithm of y cap. So y is the real value of y, and here there should be I, and here I runs from 1 to c if there are c number of classes. Now this is the short version of the formula for cross entropy loss, and y cap is the predicted value of y, and just the y, it's an actual label, actual value of y. Now let's expand this summation term in case of binary classification. So you have two classes. So if y is the probability for if y is the probability for something to be in class 0, then the probability for the same thing to be in class 1 will be 1 minus y. So here it's very easy to write an expanded version. So here the expanded version will be minus y times ln or natural logarithm of y cap, which is what this equation is already saying, minus, do you see what this is? This is 1 minus y, which is the probability for the, this is the probability for the data point to be in class, in the first class, and 1 minus y is the probability for the data point to be in the opposite class. And if the prediction probability y cap for the particular data point to be in the class 1 is y cap, then the probability for it to be in class 2 is 1 minus y cap. So the fairly straightforward expanded version of the cross entropy loss is like this: minus y times logarithm of y cap minus 1 minus y times logarithm of 1 minus y cap. Now what is y cap? Y cap is the prediction. And what is prediction? Prediction is nothing but sigma of z. This is equal to y cap. So here I'm replacing y cap with sigma. Same thing, same equation. So this is what loss? This is not mean squared error. This is cross entropy loss. Now, once we have the cross entropy loss, again, let's see how the loss function's derivative look like this time. Previously, we saw that the dou loss by dou z, which is also same as dou mean squared error by dou z, was having this format, and it had the vanishing gradient issue. What if we have cross entropy loss? In cross entropy loss, we can easily calculate the mathematical form for this loss. So dou by dou z of this is what? Firstly, let me just write for the convenience, for your convenience here, that z sigma equal to 1 by 1 plus e raised to minus z, right? So now dou by dou z of loss is minus y by sigma, because derivative of logarithm of something is 1 by that times sigma prime of z plus 1 minus y. And here, why do we have minus changing to plus? Because here you have 1 minus sigma. So ideally, or you could have written this as just minus, write it like this, minus 1 minus y divided by whatever is there inside the logarithm times minus sigma prime of z, because derivative of 1 minus sigma is minus sigma prime of z. But then you can cancel this minus and minus to make this into plus, and you can delete this minus sign. So this will be the form of the derivative of loss with respect to z. Now here, sigma prime, we have already calculated. Sigma prime is dou sigma by dou z equal to sigma times 1 minus sigma. We have already calculated, I think somewhere up here. Where is that? Yeah, this one. We have already calculated that d sigma by dz or dou sigma by dou z is sigma times 1 minus sigma. So we can substitute that here. Fairly simple calculation. So we substitute that here to get, so if we substitute sigma prime to be sigma times 1 minus sigma, the sigma in the denominator and numerator will get cancelled. And then this whole term will become like this. Minus y times 1 minus sigma. Similarly, if we substitute for this sigma times 1 minus sigma, this 1 minus sigma in the denominator and this 1 minus sigma in the numerator will cancel and only sigma will remain. So this term will become sigma times 1 minus y. That is this guy. So now this is the final format of the loss function derivative. Dou loss by dou z is equal to minus y times 1 minus y cap. Why did I suddenly write y cap here? Because sigma is y cap. Y cap, which is the predicted value of y, is equal to sigma of z. That's why I have replaced sigma with y cap. So this will be minus y times 1 minus y cap plus 1 minus y times y cap. This is telling us a lot because see, now let's pause a moment and let's try to understand what are we trying to do here. When do you want to maximize the loss? When will you say that your model is really, really bad? Your model is very bad if the actual value of y is 0, but the predicted value of y is close to 1. Then you have a bad model. Then the loss should be ideally high. Similarly, when is there any other case when the model is bad? Yes. If the value of y is actual value of y is 1, but the predicted value y cap is close to 0, then also the model is very bad. So let's imagine that the actual value of y is 1 for a moment, which means the model ideally should predict y cap being close to 1, which means if y cap equal to, let's say 0.99, which is fairly close to 1, then the amount of change that we should bring to w or b, which are the parameters that we are trying to optimize, should be very small, which means the rate of change of loss with respect to z should be negligible or very small. So here let's substitute these numbers. So y equal to 1 means this term is gone. If y equal to 1, this term will not exist. And if y cap equal to 0.99, 1 minus y cap will be 0.01. And minus y means it will be minus 1. So it will be minus 1 times 0.01, which will be minus 0.0. So the term dou loss by dou z is very small. So you are not penalizing the parameters w and b that much. What if y cap equal to 0.01? Then you have to penalize y because the real value of y is 1, but you are predicting 0.01. Now let's substitute 0.01 here. Now if you substitute 0.01, 1 minus, so y is 1, right? So this term is again gone because this term won't exist because y equal to 1. These two term 1 minus 1 will be 0. But then you put y equal to 1 here. So it will be minus 1 times 1 minus 0.01, which will be minus 0.99. So this is a big value in the gradient. So you are penalizing now w and b because the change that you will bring to w is nothing but w will be assigned to be w minus eta times dou loss by dou w. Now you might be wondering, here we are calculating only dou loss by dou z. We are not calculating dou loss by dou w. So how come dou loss by dou z's value being small affect dou loss by dou w? Because they are directly related. See, z equal to w x plus b, which means dou z by dou b is dou loss by dou z equal to, or rather maybe dou loss by dou b equal to dou loss by dou z times, using chain rule, dou z by dou b, and dou z by dou b is 1. So this is same as dou loss by dou z. So to calculate a change in loss with respect to b, you just need to have directly the change in loss with respect to z. Then how about dou loss by dou w equal to dou loss by dou z times dou z by dou w equal to, so dou loss by dou z we already know because we are calculating that from the loss function formula. Dou z by dou w is x. So this will be dou loss by dou z times x, right? So this is the value of, this is how dou loss by dou w is directly related to dou loss by dou z, and this is how dou loss by dou b is directly related to dou loss by dou z. So calculating dou loss by dou z is essentially calculating the other two terms. So, but now, okay, these are the two cases when y equal to 1. What if y equal to 0? If y equal to 0, your prediction should be very close to 0. You don't want y cap to be like close to 1. If that was the case, you should penalize, and let's see if that will happen. If y cap equal to 0.99 while y being 0, then y being 0 means this term will not exist. This term will be 0 because y equal to 0. Then this term will be 1 and y cap is 0.99, which means dou loss by dou z is 1 times 0.99, and this is a high value. So you are penalizing w and b by making it change a lot. If y cap equal to 0.01, the prediction is very close to the actual value, then you should not penalize too much. Then dou loss by dou z equal to 1 minus 0.99, sorry, 1 minus 1 minus 0 times 0.01. So it will be 0.01. So this change is small. So you're not penalizing too much. You're not penalizing the parameters too much to push them to change. So the penalization is appropriate and there is no vanishing gradient problem. So this is the reason why cross entropy loss is used in, for example, in problems like classification, especially in logistic regression. So now what we can do is we can try to appreciate logistic regression a little bit through a numerical example. Still, we are not going to code right now. Here, I just want to show you a numerical example using Excel sheet from scratch. And after that, we can code this same thing using simple logic in Julia from scratch. So let's get into that. So now let's implement logistic regression in this Excel sheet. And here we'll be implementing the exact same logic, but instead of using a programming language like Python or Julia, we directly implement the formula in Excel sheet. So we have only 2 data points. The first person has a glucose level 90. This person is not diabetic. Second person has glucose level of 180 and this person is diabetic. Let's imagine that, this is a very bad training data set because you don't have that much data. But for the ease of implementation here, let's just assume that this is the case. Now, what all do we need? We need W, we need B, because W X plus B equal to Z, right? Then we need, we can also calculate, I guess, loss, maybe. Then we have, actually, before coming to loss, we have D loss by dz for person 1. And why am I writing person 1? Because the loss might be higher for first person and lower for second person depending on the value of their x. X is like the glucose level itself, and their y, which is diabetic or non-diabetic. So d loss by dz for person 1 and d loss by dz for person 2. And now what do we need? We need d loss by dw, and this is the total value, and d loss by db, right? We are calculating these many things, and we also have to define a learning rate. Let's say the learning rate is 0.001, whatever. We're just starting with something random. So now we will start with initial values of w. Let's say initially w is 0 and b is 0. So I can put these columns in some color so that you can see it. So W initial value is 0, B initial value is 0. And what is D loss by dz? We have already written the equation here. D loss by dz equal to minus y times 1 minus sigma plus 1 minus y times sigma. Now for the first person, the y value is 0 because this is the real value. So this equal to minus y, sorry, we should type equal to minus y times 1 minus sigma is what? 1 by 1 plus exponent of minus x. And what is minus x? Exponent of minus wx plus b, right? So w is this guy, w times x is what? X is this glucose level, plus b is what? B is this. So this is the first term. This is the minus y times 1 minus sigma term. Now let's add the next term. Plus next term is 1 minus y times sigma. So 1 minus y, 1 minus y times sigma. Sigma is 1 by 1 plus should put this in bracket 1 by 1 plus exponent of minus x is nothing but wx plus b. So w times x. Oh no, so this is for second person. So okay, let me. No, this is still for the first person. So yeah, 1 minus this times 1 plus 1 by 1 plus exponent of minus w, which is d2 times x is this guy b2 plus c. C is the wx plus b. B is this guy. Okay, so I hope this is. I hope I have not made any mistake here. So let me see. Let me first remove this guy to see if formula has balanced brackets. Okay, bracket seems to be fine. So this is minus y times 1 minus sigma, and sigma is 1 by 1 plus e raised to minus z, and z is wx plus b. And here there is one more thing that we have to do. If you don't want to enter, formula is missing one or more open parentheses. So maybe a parenthesis is missing in this. So I'll cut this to see if actually parenthesis is missing here or not. Okay, yeah. So in this part, some parenthesis is missing, which is fine. 1 by 1 plus e raised to minus exponent of minus something. Am I having an extra parenthesis? I guess, yeah. Okay, I had an extra parenthesis, I guess. So this is for the person 1. And for person 2, the formula is exactly the same. So I'll copy the formula and then I will paste it here. But instead of B2, because this is B2 and this is B3. So person 2 is actually B3. And the Y value of person 2 is in C3. So here I will change B2 to B3, C2 to C3. But D2 and E2 I'm not going to change because W and B are the same. And C2 to C3, B2 to B3, right? I think that's all. So this is the loss, D loss by DZ for person 2. Now the loss in W happens because the person 1 contributes to the loss, person 2 also contributes to the loss. And we know that D loss by DW is equal to D loss by DZ times X. So here we can take equal to mean of two numbers or average of two numbers. What are the numbers? The numbers are D loss by DZ times X, right? Times X for the person 1, comma, D loss by DZ times X for the person 2. And this will be the average value, the mean value of the loss with respect to W, and mean value of loss with respect to B will be equal to average of these two guys, this comma this. Because if you remember, D loss by DB is same as D loss by DZ. So we just need to take the average. Fine. And that number is turning out to be 0. I'll check if there is any issue because I have already done it in sheet 1 here. So I don't want to repeat the same calculation. So that's the reason why that's the reason why I'm doing it a little bit fast, because I know that if I make a mistake, I can just copy the formula from sheet 1. Anyways, now what do we do with W? So the new value of W equal to old value of W minus learning rate, which is this guy, times D log by dW, right? The new value of B equal to the old value of B minus learning rate times D loss by dB, this guy. Okay. Now there are a few things to do, because you might know that in Excel, all you need to do is like click and drag like this. But then this will not lead to the desired results, because some columns, some cells are constant, meaning learning rate is only there in B5, right? So we have to keep wherever there is B5, that has to be constant. So we'll see how to do that. So here, first of all, learning rate is mentioned here in B5. So this I will convert to $B $5, which means in the formula, even if we click and drag, it will not go to B6, B7, etc. And here also I'll put B5, $B $5. Fine. That is the first thing. Second thing is, here I want in this column F, I'm always looking at person 1, right? Which means it will always be 2. So C2 means person 1, Y means C2. So this C2 value I can be putting in $C $2, but D2 I can put it such that 2 will become 3, 3 will become 4, etc. But D will remain the same. So I can put $D, then B2 will be $B $2, then E2 will be $E, but just 2, because 2 will become 3, 4, 5, 6, etc. Because the value of B will change. And here it will be 1 minus $C $2 divided by 1 plus exponent of $D times $D2, not $D $2. Then here it will be $B $2 plus $E2. So this part is fine. Now here $C $3, $D2, then this will be $B $3, then $E2, $C $3, $D2, $B $3, and $E2. I hope I have not made a mistake here. And here also we have to do one more thing, because in the loss calculation we are multiplying by X, and X value is always there in the fixed set of columns. So this should be $B $2 and $B $3, because that I don't want to change while clicking and dragging. So now I hope the formula is fine. If I click and drag, this should show some numbers. Fine. Okay, now some numbers are coming. Now all I need to do is like click this and drag it down, and then we will see how the change in loss is kind of what's happening to the change in loss. So this is what is happening, right? Something is happening that dou loss by dou W and dou loss by dou B looks like flipping, and the value seems to be kind of high, maybe because my learning rate is a little bit high. So what if I put one more 0? Okay, then I have fairly good numbers, looks like, because here dou loss by dou W and dou loss by dou B are kind of small numbers. And how can we know if this value of, and now what is my final W and final B? It's kind of saturating. Final value of W is this, final value of B is this. Is this fine? We can check. So let's say I define some glucose level. So these two were the original data points. Now I'll say another person with glucose level 70, another person with 50, another person with 220, another person with 100, another person with 110, and etc. etc. And if we want to make predictions, let me remove this actually. Or actually here I can put truly these two guys we knew, and now prediction. Prediction will be equal to 1 by, because we are using logistic regression, 1 by 1 plus exponent of minus W times X plus B, right? W times X plus B. So this is giving us some number, but we have to do one more thing, because W is now, we are just using this cell. So W should be $D $30, and B should be $E $30 as well, because that should not change. So now this is the prediction 0.6, and these are the predictions. Now, what does this mean? This means that if we can define, I guess, different cutoffs. It need not be always at 0.5. So if the cutoff is maybe 0.6 in logistic regression, I mean, I don't know if it makes sense to do that, but there are various things you can try. Here, one thing that definitely makes sense is if the value of logistic regression is high, it is corresponding to high value of glucose. So diabetic then equal to 2 of this greater than, let's say, 0.6, then it's diabetic, let's say. Okay, I guess there is something. true returns logical value of true. Maybe I just need to put the expression. I don't need to put true or false. Okay, true. Now, true, true, false, false, true, true, true. So which means this guy is diabetic, this guy is diabetic, these two are not diabetic, and these three guys are diabetic. And if we change this 0.6 to, let's say, 0.55, how about now? Because this guy in reality is not diabetic. So, okay, not 0.55 because we want to increase the cutoff. So let's say 0.65. Now, hopefully, now let me put non-diabetic guys in green. This is also not a good cutoff, I guess. So maybe 6.2. How about this guy? I'm literally manipulating numbers right now, but false, 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 false. So now this regression model, logistic regression model is saying that these four guys are not diabetic and these three guys are diabetic. I'm not using a 0.5 cutoff here. I'm using like 0.62 as the cutoff. But anyways, so this is a basic example of how to build a regression model. Here I used a Excel sheet, and I hope there are no mistakes in my formula. If there is, maybe that is reflecting in my final result. But I hope you get the gist of it. I hope you understand how to modify W and D. And then now, if we had 100 or 10 people, the reason why I only selected 2 people is because I have to calculate the loss for both people, right? But then if I had 10 people, I'll have to calculate 10 losses. So that's the reason why I restricted to 2. I did not want to do too many calculations. But I hope this is generalizable enough for you. You can extend the understanding here into any number of cases. All right. So now what we can do is we can come back to our implementation in Julia. So instead of implementing by hand, let's implement by code. So I have written the code here in blocks so that we can save some time. Instead of typing all this from scratch, we can copy paste. So basically, first is importing packages. And let me actually delete some of the, I don't think we are using plots. We are not plotting anything here. Random is a package that we are using to create random numbers as the initial weights and bias. Statistics is used for calculating mean, right? So these two packages we can import. So first, let me open a terminal. Then as usual, we open Jupyter Notebook. So Jupyter Notebook. And then on Jupyter Notebook, once it's open as a local host here, we'll open the Jupyter Lab, and there we will have a Julia Notebook. Now, obviously, you should have Jupyter Notebook, Julia, and Julia for Jupyter installed. And the way to do this is already covered in the very first lecture of the series. For any reason, if you have not done that, just go back to that and do it. It should not take you more than 5 minutes. So click View and open Jupyter Lab. And this should open fresh notebook. So click File, New, and Notebook. But I think here in my case, the default is Python. So it shows IPy kernel. So click this, and change to Julia 1.11.1. So now I'm in Julia. And here, right click, and let me rename this as Logistic Regression. Okay, fine. So now let's copy the import packages. So we'll use these two, random and statistics. I have already installed these two packages, so I don't have to use pkg.add. But if you haven't done that, here in the notebook, you will see what command to run. Fine. Now, and I'll close this for convenience. Now data. So we have certain X values and Y values. So here what we have is a data of hours studied versus pass or fail. So here 1 denotes pass, 0 denotes fail. So from this data, you can see that if someone has studied for less than 4 hours, they will fail. If someone has studied for more than 4 hours, they will pass. Fairly simple data. And this is like a classification. Now, the thing is to construct a model which will make a prediction on a new data set. For example, it could be on a completely new data point, which this thing has not seen, meaning the model has not seen. Or you can split the data set into training and testing. So here, first we normalize the data such that the data sets are between, it is centered around a mean, and it's going left to negative numbers and right to positive numbers, because we are subtracting the mean value from all the numbers. So mean of X will be here in this case 4, and you are subtracting 4. So this will become -3, -2, -1, 0, then it will be 1, 2, 3. And you don't have to normalize y because y is already categorical variable. It has only two values, 0 or 1. And you are dividing by standard deviation so that the range will become, instead of range being -3 to 3, it will become something else. It will be a shorter range. And then we split the training data, the normalized training data, into normalized data into training and testing. So X normalized, we are using 5 data points for training and another 2 data points for testing. So 1 and 7 we use for testing, and 5, 2, 3, 4, 5, 6 we use for training. And we know that the labels corresponding to 5, 2, 3, 4, 5, 6 are corresponding to 5. We have 1. Corresponding to 2, we have 0. Corresponding to 3, we have 0. 4, we have 1. And 6, we have 1. For 1 and 7, we know the output is 0. Corresponding to 1 and corresponding to 7, the output is 1. So ideally, in the testing, the prediction should be something like 0, 1. Because corresponding to 1, it should predict 0. And corresponding to 7, it should predict 1. And let's see if this will happen or not. So I'll copy this code and paste it here. So this will define the data set. Now, after defining the data set, we need a few functions. So definition of sigmoid. Sigmoid is literally the output itself. So y bar or y cap, not bar, y cap equal to 1 by 1 minus e raised to minus z, right? And here initialize parameter. So this is where we use the rand function. And this is why we need this guy random package. So this rand function will generate random set of weights. Bias, we are initializing it as 0. I think you can also initialize this simply as 0, but doesn't matter. This will return weights and bias depending on the number of features. And we'll see how to call this function. So we have sigmoid. We have the initialize parameters, which is only used once. Sigmoid will be used for every single, it will be used every single time. Then we compute the prediction. So compute z equal to w x plus b, right? That's what we said. So z equal to w x plus b and y cap equal to 1 by 1 plus e raised to minus z. So first we will call this function, then we will call the sigmoid function. First we will initialize parameters, then we will compute this, then we will call sigmoid. And after that, we'll compute loss. And loss is, here we are taking mean, because if there are 10 number of people, we'll be taking the loss with respect to loss of everyone, and we'll calculate the mean. And loss we have already defined. So loss was y times logarithm of y predicted. This is cross entropy loss, plus 1 minus y times logarithm of 1 minus y predicted. There are two classes. That's why you have only two terms in the cross entropy loss. Otherwise, if you have 5 classes, you will have 5 such terms. But the idea here is that you see this dot means you are taking it element wise. So dot times y log dot of that 1 dot minus y dot plus. So you are doing this operation element wise. So let me copy paste some of this so that we can slowly start implementing this one by one. So first let me copy sigmoid. Sigmoid we are not calling, so it will not return anything yet. Then initialization of parameters. Then computing the z value, sigmoid of z value. So this is the final prediction itself. So here you are returning not just z, you're returning sigmoid of z. And then you are defining the loss function. Then gradient descent. Okay. So here, let's see what we are doing. Now implementing the gradient descent. Here we are defining epochs, which we did not discuss in the Google Sheet implementation, but we can do that, which is very common thing to do in machine learning. And predictions, here we are calling the predict function with weights, bias, and input. And this predict function we have already looked here. It's literally returning sigmoid of basically 1 by 1 plus e raised to minus wx plus b. That is what it's returning. And that is the predicted y cap. And that error is nothing but predictions minus y. Now here you might be wondering where this came from. And because the gradient weights, the d by dou loss by dou gradient, this guy, dou loss by not dou gradient, dou w, and dou loss by dou b was defined such that this is equal to dou loss by dou z times X. And this was equal to dou loss by dou Z itself. Now, what is this? Dou loss by dou Z, we had calculated here for cross entropy loss, it was of this form. So dou loss by dou Z was equal to minus y times 1 minus y cap plus 1 minus y times y cap. And now we can expand this. This is minus y plus y cap y plus y cap minus y cap. So this and this term will cancel, and this will be y cap minus y. And this is prediction minus actual value. And you can see that here the error term is that prediction minus actual value. Although this is in matrix format, we are basically for individual values, we are subtracting predicted value of y, which is y cap minus y. So that is this line. Now here we are doing x prime times error divided by size of x comma 1, and this is nothing but you are calculating the mean value of the losses with respect to mean value of the gradient of loss with respect to W. So what we did for in the Excel sheet was we took the mean value. There were only 2 people, so the mean value was just average of the loss, dou loss by dou W for person 1 plus dou loss by dou W of person 2 divided by 2. But here we are calculating similar thing, and for bias, since dou loss by dou Z and dou loss by dou B are the same, we just need to simply calculate it and get the mean value. So that is this. And then we update the weights and bias, and you see this is not equal to, this is minus equal to. Minus equal to means weights. It's same as writing weights equal to weights minus learning rate times gradient weights, and bias equal to bias minus learning rate, which is eta times gradient bias, right? So that is these two lines, and then we return, we do it over certain number of epochs. Actually, the epochs, number of epochs were the number of steps that we did. In our Excel sheet case, I think we dragged it all the way till 100 epochs or something like that. So let us copy this piece of code, this block of code, paste it here, and it will not do anything because we are not calling the function yet. Now we train the model. So here in the training, the weights comma bias initial values are initialized using the parameters within the within this random function. So weights were randomly assigned and bias was initially assigned to be 0 over here, rand, and the bias was 0. And then we perform gradient descent to modify the weights and bias. So we can copy paste that. So we have performed the epochs to be 1000. So this thing will run 1000 times. And okay, the function express does not exist, but no method. Okay, this is happening because it is not defined for this combination of argument types. Exponent is used in sigmoid. Yeah, I think this is because we have to x dot of minus plus. This should be done element wise. So I think that's why this error is coming. We can try running this again. Gradient weights not defined in main. Gradient weights is not defined because maybe this is this guy. And okay, now it seems to be working. Now let's make a prediction because we are going to be predicting on the test data. So in the model evaluation, we are predicting on test data with the latest values of weights and bias, and cutoff we are setting at 0.5. This we can set at whatever we want. And accuracy is basically accuracy for all data points in the test. We had only 2 data points in the test. The first data point was test at index 1, which was x equal to 1 and y equal to 0. Second was at index 7, x equal to 7 and y equal to 0. And let us copy the last code for model evaluation. And we can paste it here. Accuracy is 1. I am just interested to see this predicted values of y. So y predicted is 0, 1. Okay, perfect. So I hope you understand what's happening here. So the y predicted is 0, 1 because, okay, one more thing we can do. We can simply try to print this. Let's see what this 0.11 and 0.94. So what's happening is for the test data set, which includes 1 and 7, which is this and this, the prediction instead of 0, it is 0.11. And the prediction for this data set, instead of 1, we have 0.8, 0.94, right? So what's happening here is the model is predicting that if some student has studied for only 1 hour, their chances of passing the test is 0.11, which means they have 0.89% chance of failing. Now, this is corresponding to a student who studied for 7 hours. So what this is saying is if a student has studied for 7 hours, their chance of passing the test is 94.9% or chance of failing is 5.1%. And we can convert this into just a basic binary classification by defining a threshold cutoff. And here we are defining it to be 0.5. That's the reason why if we simply print y predicted, it will show like this will be brought down to 0, and this will be brought up to 1, because anything above 0.5 we classify as 1, anything below 0.5 we classify as 0, and that's what is happening. But I hope you understand the gist of implementation here. This is completely from scratch. We did not use any module. Actually, I don't even think we need this rand. We can probably initialize this to be just zeros, how about this? This also might very well work. Let's see. Element by subtraction. Okay, so probably what we have to do is 0 times. Maybe this will hopefully make it into, this will not bring any dimensionality issues. Okay, accuracy, prediction. I just want to print this initialized parameter size of x prime comma 2. I think this is 5 by 2, right? Size of x prime comma 2 is 1. That is x prime is 5 by 1, and yeah. So size along the other dimension, fine. There's only one feature, fine. And all we need to do is, I just want to see if this is one element vector float. Okay, so this is 0.0 times that. Okay, fine. How about this? So we are implementing gradient descent and making prediction. It's coming out to be pretty much the same. And here, if we do only 10 epochs, the accuracy won't be that good. Yeah, you see, if we run only 10 epochs, the accuracy is like you're barely escaping, because the first guy is predicted to be 0.49% chance of passing. Second guy who studied for 7 hours, 0.51% for passing. This is not 1 minus. Okay, this is not 1 minus. It's like this is a bad model. So the model is not able to predict for two extreme conditions: 1 hour of studying, 7 hours of studying. Model should be ideally be able to predict it with so high confidence, but model is being very, very poor performer here. If it is 100 epochs, I think this should be fairly better. Okay, see, when you run 100 epochs, the learning is better. With 0.43, this is saying the guy who studied 1 hour will fail. Sorry, will pass with 43% chance. The guy who studied 7 hours will pass with 61% chance. And if this is 1,000, then the values are fairly good. Then 11 and 94% respectively. What if this is 10,000? Maybe this will be even better. See, okay, amazing. So if somebody with 10,000 iterations or 10,000 epochs, the convergence of this logistic regression model is very, very good, because for a person who studied for 1 hour is definitely failing, because the data set is clearly saying that. Not this, because we are using this for testing, but in general, the trend from the data set is that 1 is on the lower end of the spectrum, which means the person should definitely fail. 7 is on the upper end of the spectrum, which means the person should definitely pass. And that is indeed what is happening. And look at the prediction accuracy. And I think if I add one more zero, this will be even better. So this clearly demonstrates, see, this is negligibly low number, almost zero and almost one. So I hope this brings fairly good clarity to you about logistic regression, not just from a mathematical point of view, which is great to understand. I hope you also understand the logic behind why we are using cross entropy instead of mean squared error. And you also, I hope, fairly well understood the from scratch implementation on code. I highly recommend you to try the same thing. It's fairly simple, but try to derive the expression for the dou loss by dou z, especially for both cases when you have mean squared error versus when you have the categorical, I mean, cross entropy loss. So please try that. That will give you very good confidence. And before ending the lecture, let me take, as usual, a moment to congratulate you for reaching this part of the course, because it's not easy to cover lectures after lecture. You are really, laying brick by brick, as I always say, for the foundations towards machine learning. And here in Julia, you are getting fairly good command over various ML models. We covered linear regression in the last lecture. In this lecture, we covered logistic regression. In the next lecture, we'll be covering k-means clustering. And with a couple more modules, we'll be wrapping up the ML for Julia part, and then we'll be moving on to deep learning. So thank you so much for listening. We'll meet again in another lecture. Take care until then. Bye.